Hello, all my genius student. Today we are in lecture number 60. Okay, lecture number 60. Of which chapter? Chapter 5, Magnetism and Matter. Alright, yes. Finally we got this lecture number 50. So, in today's lecture, in last lecture, what we have studied about the properties of magnets and the magnetic material. We have already studied about the SI unit of magnetic field, that is the magnetic field density also, that is the Tesla, alright, and the Gauss also. Today we will start a topic, the force between two magnetic pole. Alright, force between two magnetic pole of a magnet, and that is mentioned in the book as named Coulomb's law. This is very easy, my dear students. As you have been studied the force between two point charges, in same way you have to apply here the force between two poles of the magnet, and that is the Coulomb's law. So give the heading, force between two magnetic poles. Two magnetic poles. All right, yes. Directly we start our lecture without losing the time. Here we are having the two poles. Suppose this is the north pole and the pole strength is M1. At some separation, another pole it is kept. Suppose the pole strength is M2, and this is the south pole, and the two are separated by the distance R. Alright. Now we know that here the two are of opposite nature, then this north will attract it towards south and south will attract it towards north. It means if you will write the direction of force, you will find here the direction of force in this way. And for this force we are going to apply the law. This is the Coulomb's law of magnetic force between the two material pole. All right, and according to that law, this force is directly proportional to the product of pole strength. Remember, M1 and M2. Let me write here, M1 and M2 are pole strength of magnet. We are focused to the bar magnet. All right, that's pole strength. According to this law, it is inversely proportional to the R square. It is based on the inverse square law, my dear students. Altogether, combining these two, you can write F directly proportional to M1 M2 by R square. Don't get messed up with the law of gravitation. Okay, here the proportionality constant will be K, magnetic constant, and it is M1 M2 divided by R square. Okay, my dear students. Now the value of this K, actually this K magnetic constant, it is mu naught by 4 pi, and its numerical value is 10 to the power minus 7 Tesla meter per ampere. Okay, mu naught by 4 pi, it is equivalent to the 10 power minus 7. Anyway, this is the F is equals to K M1 M2 by R square, and M1 M2, remember this is not the mass, actually this is the pole strength of two magnet. All right, now here mu naught we have been used, my dear students. This is called the absolute permeability. We will study in very detail. This is called the absolute permeability. What will be the value of this absolute permeability? So it is the 4 pi into 10 to the power minus 7. Yes, wow, it's very easy, my dear student. You can see here the K will be multiplied with the 4 pi, and the K itself it is 10 to the power minus 7. So mu naught will be the 4 pi 10 to the power minus 7. Okay. Now we are moving towards the Remember, my dear students, if you will be given the pole strength or the two pole strength and the separation, you are having the value of this K, then you can find the force. It's quite easy. I'll give some question for the practice in group when I'll teach this one. Okay, now here, let me grab this one. Now the next topic we are going to cover here, the magnetic flux density. Give the heading, my dear students, magnetic flux density. Yes, write down magnetic flux density. The another name of that magnetic flux density is the magnetic field strength. Magnetic flux density. You can also write this is as magnetic field strength. Magnetic field strength. All right, it is represented by B. It's the magnetic field intensity, nothing much more. No? All right, and this magnetic strength or the magnetic field strength is defined as the ratio of the force and pole strength. Suppose we have studied in last chapter, that is in electrostatic, about the electric field. First we find out the electric force, and by dividing the unit charge we got the electric field. In same way here, first we'll find the force that we have already obtained using the Coulomb's law, and then we will divide by the pole strength. We will get the magnetic field intensity. All right, so you can see both are very familiar, both are very similar. It is not very difficult to remember. So you can write the definition, my student, here that this magnetic flux density or the magnetic field strength is defined as the force per unit pole strength. Force per unit pole strength. Okay, suppose you are having a pole here. Suppose the pole strength is M and this is the normal. At some distance you have to find out, at this point P, you have to find out the magnetic, the distance, it is R. All right, you have to find the magnetic strength at point P. What we have to do, we will place here a test pole. As we used to place the test charge, we will place here a test pole M0. Remember, M0. The property of this test pole will be, it should be the north pole, the first, and second, the pole strength of this test pole should be very small. All right, as we have discussed about the test charge, try to remember the magnitude of test charge was very small, so that it can experience the force by the other magnetic material. Okay, my dear student, so this is the test pole. You can, if you want to not the put, you cannot. Okay, and you will get the answer. If you don't want to put, you should not put this test pole. Now, according to the definition, we got that B field strength will be the magnetic force per unit test pole strength, that is the M0 of this one. Now, what will be the direction of force? If this is north and this is test pole strength, then this will be also north. So it will move away and the magnetic field will be outward direction. You can see here this north pole will have the magnetic field in outward direction, but here we can obtain B. Force between these two can be written as K M M0 divided by R square divided by M0, this M0. Okay, so the pole strength, the field strength, you will find here the M cancel out, mu naught by 4 pi M divided by R square. I don't think so. This is very tough to obtain. This is quite easy. Okay, now the next topic, magnetic dipole and dipole moment. We are going to study magnetic dipole, and dipole moment. Dipole moment. Okay, my dear student. Magnetic dipole, actually, it is the system. Magnetic dipole is the system. It is the system of two poles of equal strength and opposite in nature, separated by finite length, called the magnetic dipole, as we have studied the electric dipole. The electric dipole, it was, and in similar way we can express this magnetic dipole. Okay, now the magnetic dipole moment, this one, it is represented by capital M, and this magnetic dipole moment is the product of this magnetic dipole moment is the product of pole strength and the separation between two poles of the magnet. It is the vector separation. So this will be the dipole moment. Now let us look here. If this is the magnet, my dear student, if this is the magnet, okay, of north pole and south pole, the pole strength are here the M and M. We know that the pole strength must be same. So the separation between these two poles, this is called the dipole length. Okay, and for simplicity the calculation will be easy. We used to represent as the 2L, so that from the center we can use here the L and L for the simplicity. Alright, but it is the 2L, and this 2L is called the dipole length. Alright, so the dipole moment, magnetic dipole moment, M, it is equals to M times 2L. Alright, try to recall, my dear student, in current carrying loop we have studied about the magnetic dipole moment over there also, and it was represented by mu, which is also the vector quantity. Remember, this mu or M is very similar. You can represent this M by mu also. In some books it is represented by M, and in few books it is represented by mu, and it was for the current element, it was I into A. Okay, I into A. This was the magnetic dipole moment of current element. Current carrying coil will have the dipole moment, it is I times A. Okay, my dear students. Now a bar magnet, remember, a bar magnet itself a magnetic dipole. A bar magnet itself a magnetic dipole. Okay, must remember. You can write in note point. Now this is the magnitude of magnetic dipole moment. What will be the direction of magnetic dipole moment? This is also very important. Direction of magnetic dipole moment. As you have remember, the direction of electric dipole moment we always consider from negative to positive, and here in this chapter we have studied that I have been given a concept that negative charge will be compared with the south pole and positive charge will be compared with the north pole. It means here in this magnet the dipole moment will be from south to north, so the direction must be from dipole moment, direction of dipole moment must be from south to north. Okay, remember, if this is the magnet, if this is the north pole and this is the south pole, then the direction of dipole moment will be in this direction. This is the direction of dipole moment. Okay, try to remember. Okay, my dear students, this is the direction of dipole moment. Now here we go to derive the magnetic field on axis of magnet. You must remember, I hope, that we used to derive the mathematical expression for the magnetic field, the electric field due to dipole at axial point and equatorial point. Here, in same way, we are going to derive an equation for the magnetic field on axial line, okay, of a bar magnet. So you can give the heading magnetic field on axial line, B on axial line of bar magnet, okay, of bar magnet. Here, this is the bar magnet, north pole and south pole, and we have to derive the magnetic field, net magnetic field at this point P. Okay, now we are taking the positions. Suppose from center, this point, this is r distance away. How much? It is r distance away, and the length of this dipole, that is the magnetic dipole, it is 2L. Now we know that the magnetic field lines must be away from the north pole and towards the south pole. So due to north pole, at this point the magnetic field will be in this direction, so I'm writing here the B due to north pole, all right, and due to south pole will be in this direction, so I'm writing here the B due to south pole. The net magnetic field, you will have B net, it will be B north minus B south, okay, this one. Now we have to calculate, and what is the formula of magnetic field? We have calculated the mu naught m by 4 pi r square. That was the formula. So here mu naught and m will be common for both the pole if the same magnet, and 4 pi. Okay, now this separation for this pole, north pole, it is L plus R. So the 1 by L plus R whole square minus BS, it is R minus L, 1 by R minus L whole square. All right. Now mu naught m, now it is all about the calculation, taking LCM, L plus R whole square, R minus L whole square. So it is R square plus L square minus 2RL minus here L square minus R square minus 2RL. Okay, something will cancel out, R square and L square, minus 4R. We will have M times minus 4RL divided by, this will be the 4 pi and R square minus L square whole square, R square minus L square to the square. Direction we are getting here the I cap. All right, yes. Now my dear students, you can see we know that the magnetic dipole moment is the m times 2L. This is the length of dipole. So the m times 4L, it is the 2L. So the m times 2L will be the capital M, magnetic dipole moment. So the mu naught m, what will have the rest things? So the 2R, okay, 2R divided by 4 pi R square minus L square whole square, and this minus can be taken out with the direction, so the I cap, we can write this one. Okay, my dear friends, now we are going to proceed for the short dipole. If we are having a magnet very short length, but this is the magnetic field at axial point. For short dipole, short dipole, this length will be much smaller than the r, and so that we can neglect this L. If we neglect this L, we will have the r to the power 4 and this will be cancelled out, so the RQ. It means net magnetic field, you will have mu naught M, okay, and this 2 will be out, and by 4 pi r q, and direction is minus I. This is the magnetic field for short bar magnet, where at axial point. So must remember, at axial point the magnetic field will be 2 times mu naught m by, and this m is also magnetic dipole moment vector quantity, mu naught m by 4 pi x q. Okay, remember this result. And the next thing, try to visualize, my dear student. Here the magnetic field we are getting in this direction. All right, we are getting magnetic field in this direction B. And what is the direction of dipole moment? So we are getting the direction of dipole moment, it is from south to north, so the same. So in case of axial line, at the axial point, the net magnetic field must be obtained towards the dipole moment. Okay, must be obtained towards the dipole moment. Must remember this one. Okay, now the next. Magnetic field due to magnet on equatorial line. Okay, the second one, B on equatorial line. Equatorial line. Okay, my dear student. Now, if I'll give you the hint to solve this one, I'm sure you can solve. So I'm giving you the hint only. All right, and you will derive by yourself. This is north and south. This is the center. Dipole length 12. We are going to find out here the magnetic field. Okay, my dear student. And this length, suppose it is R. We know that due to this pole there will be a magnetic field at this point, and due to this pole also there will be a magnetic field at this point. Okay, due to north pole we will have the magnetic field in this direction, and due to south pole the magnetic field will be in this direction towards. Okay, when you will draw here the proper axis, you will find this magnetic field have the two component, one along this one and one along down, and this magnetic field also will have the two component, and the few over this axis it will be cancelled out. The net magnetic field will be obtained in this direction. Yes, am I right? Yes, the net magnetic field will be, you will get in this direction. And this distance, if it is 2L, then this will be the L, and this is R already. So this distance, if it is Z, then Z can be written the root under R square plus L square. Here this Z is also R square plus L square. You will have to use while finding the magnetic field. After finding the magnetic field, you suppose here the angle theta, because the component you are breaking here along with the theta, sin theta and cos theta, you need to find the value. So using this one, this triangle, you can find the sin theta and cos theta. All together you will find an equation. You have to shorten that equation using the concept of short dipole. In short dipole, in case of short dipole, this length L will be much smaller than the R, and that L will be cancelled out, and you will find result mu naught M. In case of this equatorial, mu naught M by 4 pi RQ, and direction will be I cap. This will be your result. Try to find by yourself, my dear students. Okay, one more derivation, and this is your homework. Remember, this is not the result I have been obtained here. This is your homework. Try to complete it. Never leave any derivation in middle. Now the next one, the homework for you. The next homework, my dear students, it is, if you are supposed to ask the magnetic field at arbitrary point, as we have discussed in case of electric dipole also. So this is your homework. This is the north pole, this is the south pole of the pole strength, same, it is M. Okay, from the center I'm not taking any arbitrary point or the axial point, but I'm taking any point in the space, and you have, at a distance r, you have to find net magnetic field at point P. This is your question. All right, you have to find net magnetic field at point P. As I have explained you, I have just taught you in last chapter that to just break the dipole moment in two direction. One, it is perpendicular, and this dipole moment works as the equatorial. This point will be now equatorial to this dipole, and one component will be break in this direction, and then for this dipole moment this point will be considered as the axial point, and then you will have the two dipole filled over here due to the dipole, and you will get the resultant. Okay, my dear student, in this way. Now the two more topic you should do your exercise. Let me recall you why I'm giving this all are in homework, because I told you this is very similar to the chapter in electrostatic that you have studied already. Okay, so the next one is the torque. Okay, torque on a bar magnet placed in uniform magnetic field. Again, I'm helping you, giving you the hint how you have to solve. Here, this is the uniform magnetic field. If you place a bar magnet over here, what will happen? If this is north pole and this is south pole, from center it will start moving. It will experience a force. This will experience a force opposite to the field, and this will experience a force in direction of the field. We know that force per unit pole strength is the magnetic field. It means the force can be written as the pole strength into magnetic field, and this pole strength, suppose M, sorry, not M1, M, and this is also M. It means this pole will experience a force in upward direction, how much? MB, and this will also experience a force, how much? It is MB. Finally, it will rotate in a particular direction, suppose this is the theta, all right, and then you will find the torque using the concept of electrostat that I have been explained already. Now, you will find the result of this torque. I am writing the result. Tau equals to MB sine theta. You will get this answer. Now the next homework. All you have to do, my dear student, the next homework is to find the work done to rotate. If you rotate a dipole, suppose this dipole, it is not in stable equilibrium. As soon as you will leave this dipole, it will rotate, and after going in this direction, it will be in stable equilibrium. It means if any dipole, it is in a stable equilibrium, to rotate by some angle, we need to do some work. Actually, we are going to study here what will be the amount of work done to rotate a dipole, and that we have studied the work done to rotate an electric dipole. Here we are considering the work done to rotate a magnetic dipole. You will do by yourself. So give the heading work done to rotate a dipole. Work done to rotate a dipole. All right, we know that the small amount of work done, it is tau d theta. Okay, already you are having the tau here, we have been considered, and d theta. After integration, you will find a result. W is equals to, I am writing the result, my dear student. Let me write the result by the red marker. You have to reach over here. W, you will find it is mu at the M. This is the M. M B 1 minus cos theta. You will get this result. All right, yes, this will be the result. You can also study the potential energy, my dear students. You can also study the potential energy, and you will find the potential energy. It is minus potential energy will be, let me write over here. You can do the practice for that one also. Potential energy you will find minus m dot b. In electrostatic it was minus mu dot E. Here you will find minus m dot b. This is the potential energy. Okay. After completing up to here, I will teach you, if you will place a dipole in uniform magnetic field, not in perfect stable, that is unstable, then it will start rotating. Or if you placed a dipole in stable equilibrium, suppose it is in a stable equilibrium, by disturbing very slightly, it is again try to regain its original condition, that is the stable equilibrium, and due to inertia it will start oscillating, this one, like a oscillator. All right, you have to find the time period of oscillation, that we will study in next class. That is the oscillation of dipole placed in uniform magnetic field. So this is all about today's lecture, my dear students. Thank you very much.